Hello, students. I want to share with you one of my favorite applications for understanding gravity. It's a simulation that I don't think is going to be supported by my computer very much longer, and it does not run on the iPad. So with no further ado, let me go ahead and show this thing to you. Take this thing off the screen so I can get to my buttons. That work? Come on. There we go. Okay, so basically what this allows us to do is if you look down at the bottom left corner on the screen, you'll see I can select different amounts of mass to place wherever I want on this screen, which is basically representing like space without any nearby stars or anything. I don't know if that really exists in terms of there always being something with mass in some distance away that's, well, as you'll see, will affect the motion or at least the force that is influencing the behavior of an object or a body in space. So we'll go ahead and start with huge, and you'll notice that it's showing a mass value of 1 million right here, 1 with 6 zeros. It doesn't give a unit. We can treat it as millions of kilograms, so this would be a million kilograms. But from this point forward, I'm just going to use the number without the units, which I hate to do. I think it's always a good practice to use units. But we have a mass of 1 million, and it shows as a red dot. You can see that now on the screen, I hope. And as you can also observe, it's not doing anything. However, what I want you to start thinking about is what would happen is if I were to take another huge 1 million mass of 1 million and place it nearby. Let's say right around here. Okay, so go ahead and pause the video and think to yourselves or discuss in your class, if you're using this in a class right now, what will happen when I go ahead and place a second mass right here where my cursor is. Okay, pause the video, come back when you have your guess. Welcome back. I'm going to go ahead and place the mass, and we'll see if your predictions were correct. Boom. All right. So some of you may have predicted what we just saw. Others of you may have said they didn't think anything would happen, and others still would have said something about orbits, that they would have gone into orbit with each other. I want you to think for a moment about why they did what they did. They just went straight toward one another. They increased their speed at the same rate. They started out slowly, and then they got together quicker and quicker, so they were accelerating towards each other. And they ended up right in the middle of between the two locations where they started. We're going to do the same thing again, only this time we're going to have our huge mass right here, and we're going to put a large mass, which is, instead of a mass of 1 million, it's a mass of 100,000. And I'm going to go ahead and place it here. It's a smaller mass. It'll be a smaller sized body. And go ahead and pause so you can make your prediction and think of what will be different this time around. Okay, welcome back. And here we go. All right. So I hope many of you had a prediction along those lines that they would, again, go straight toward one another. The difference on this one was that the smaller mass did a lot more of the acceleration and a lot more of the distance traveled. And I want you to think back to Newton's second law, if you didn't already have that in mind when you were predicting what would happen, that force equals mass times acceleration. And remember, any two objects that are exerting a gravitational pull on one another have the same gravitational force on one another. And so even though it's a smaller object, it's being pulled with the same amount of force as the larger object. But that same force with a greater mass is going to mean a smaller acceleration. And the smaller mass, I don't know if you can see my hands, it's not showing my little screen here, would be a greater acceleration. As mass goes up, acceleration must go down if the force is the same, and vice versa. Okay, so one more example like this, and then we'll move on to what I think is the coolest thing. So we'll go ahead and create another huge 1 million, mass of 1 million object. And now this time with our large object, instead of sending it, placing it motionless in space and allowing gravity to have its effect, we're going to give it some initial push. We're going to give it an initial velocity vector. And if you notice, I don't know if it'll show up on your screens, there's a blue vector that's formed, or an arrow, as I move my cursor away from where I just clicked it. So I can make it a very small initial velocity like this. We'll try that. And what you'll see is that instead of continuing in a straight path, gravity is affecting it just like earlier, only now it crashed. It crashed again. But this time, there was a curve to the motion because that initial speed allowed it to move towards, well, what we would know is an orbital path. And you've already seen this with I believe most of you will have seen already, the thought experiment, courtesy of Isaac Newton several hundred years ago, who came up with this idea that if you had a tall enough mountain and a powerful enough cannon, and you kept launching cannonballs faster and faster, at some point the ball would be moving so fast it would never hit the Earth. It would just go into an orbit. And that's essentially what we're doing here with any two objects. So let's go ahead and do the exact same thing again. I'll put my the mass that is 1 million right there, and I will take my large object with 100,000 mass, and I will give it a greater initial velocity. And let's see how this one behaves. And we have an orbit. But what you should also notice is that our large mass, the 1 million kilograms, is also being affected by the large mass, by the 100,000. And so the two of them are not actually staying static in space. Together, they're all going to be affecting each other. And that initial motion that I gave it, moving upwards, essentially is now influencing both objects. And the two of them together are continuing upward. And those will continue for some time. So now, I mentioned the last thing that I was really excited about with this application, and here it is. If you notice this button at the bottom left corner, it says Generate Protodisk. Proto meaning like before, like like a prototype or a protoplasm. Essentially, what we're able to do is I didn't show you that we can select masses as small as 1 million kilograms, I guess, 1 times a million kilograms. But the unit of mass is just 1, so that's 1/millionth of what we started with. And they would behave the same way. If I wanted to put a dot here and a dot here, they'll just go towards each other like before. But it'll take a little longer because there's less mass involved, so the force isn't as great. But what happens if I click this bottom button on the left is that it'll take somewhere between 800 and 1,500 or so. It just kind of randomly generates a number of these single value mass objects and just throws them onto the screen. And usually they're in a disk shape, take up about a quarter of the screen. And there is no other force or no other action between these objects other than gravity itself. Essentially, this program, this application that we're using right now, will apply the mathematics of gravity, the way in which an object based on its mass and its distance will affect another body based on its mass. And it calculates for all of these objects all at once. And I want you to watch what happens. Actually, I'm going to pause it right after I put them up there, and then I want you, because it'll help you visualize, and then I'll pause it and have you think about it, okay? Actually, I don't know if it lets me pause it. Okay. Well, here goes. Please feel free to hit pause right after the disk appears to think about what you think is going to happen. Here we go. I've turned off the part of this program that shows the little paths because then it goes way, way too slowly. So what you may or may not have noticed was that I didn't actually notice myself the initial number of particles. It gives a total particle count right down here. But there was some very large number of particles at the very beginning, and it went down fairly quickly. It's actually still going down, but more slowly. It's at 42. Now it's at 41. Now it's at 40, 20, 39. And you could probably figure out just from watching what's on the screen why that number's going down. So think about that for a moment before I sort of answer it. Okay, I'm actually going to go ahead and tell it to show us the paths of these objects, which will slow everything down, but allow you to see what's happening. Now, the first question I'm going to ask you, and then ask you to pause the video and then think about and answer, is why did this happen? What happened to all the small particles? Why is it that we ended up with some large ones and some small ones and a bunch of different sizes in between, and that they're in all different places? So go ahead and pause, think about why we have what we have on the screen now. All right, welcome back. And the last question I want you to think about is, what caused them to go into orbit? What caused them to be going in the direction they're going? At least most of them right now are going around the central objects. So go ahead and pause and think about that, and then we'll come back. All right, welcome back. So yeah, to wrap this up, I just want you to think about what you're seeing here. The objects that are now orbiting around this central set of masses, it turns out we actually have what we could call a binary star system. We have a huge and a very large object in the middle, and then we have a bunch of much smaller objects that are orbiting around them. And what happened was, at the very beginning, gravity and nothing else pulled all these objects into each other. There was no motion until gravity started that motion of them colliding into each other, of being pulled into each other. As soon as those collisions started taking place, the objects started going every which way. Somehow we ended up with them all going in one direction, this counterclockwise path from our vantage point around the central bodies. And if you think about, if any of you, or you've seen perhaps in the movies, you've been to a roller rink or an ice rink, and you and everyone else on the rink is skating in the same direction. Imagine if for some reason, let's say you wiped out and you got up a little disoriented and started going the wrong direction. Well, you're going to be going down again really soon and probably taking some other people with you, because it's a lot harder not to crash if you're going against the traffic, so to say. And so what we're looking at right here are a bunch of masses that are left over from these initial collisions. Most of them that were going the other direction got destroyed, and the resulting motion, the masses that survived from those initial collisions and then the subsequent collisions, were now down to 29 particles. That is what we have now. These objects that are still in motion will stay in motion. The fact that, from Newton's first law of motion, that an object at rest will stay at rest, an object in motion will stay in motion, is that these objects will continue to move continuously in a straight line unless acted on by another force. And if the only other force acting on these objects is gravity, the gravity is not slowing down their circular motion or their elliptical motion. It's only changing the direction of that motion, because they're going too fast to ever crash into anything. And so they will continue merrily around in their circular path at a constant speed if it is truly circular. Or, as you may notice for some of these objects that are moving in a much longer elliptical path, they'll speed up as they get closer to the mass because the force is getting higher. And then they'll slow down as they get further away because the force is getting lower. And remember, mass times acceleration equals force. So the force will be decreasing, then the acceleration needs to be decreasing. So I'll let this run for just a few more moments, and then if I'm smart, I can speed up the video for the last part of this before I share it with anybody. Oh, just had another collision. And then you can see the result. I'm going to go ahead and zoom in a little bit. Hopefully this won't wipe out the... There we go. That's pretty cool. And I should have pointed it out sooner, actually. There was oh,